Okay, so today's lesson, we're going to look at area and volume similarity. So if you remember, we talked about similarity with the triangles and also with, say, squares or something or whatever. So we said if we said if you've gone from 2 to 4, you know that that's a similar figure. And say this, if you're going that way, the scale factor, you've gone from, you've got your new length 4 over your original length, so it's 2, okay? So it's where we're going to look at that, but now we're going to look at 3D objects. So we're just going over here again. So the scale factor, just remember, it's the new length over the old length. So say I went from a big square to a little square. So I'm going from 4 to 2, going that way. The scale factor, the new length is 2 and the old length is 4. So the scale factor is actually a half, okay? So you've got to be careful which way. So we say new length because sometimes you don't want to say the larger object because what even if it got reduced? So just think the new length over the old length. Now, also with the scale factor, see how I'm always simplifying it? You need to do that first. So a length ratio or a scale factor has to be in its simplest form for when we use it. So if we have a look, we're going to look at how the areas and the volume compare when we've got similar figures. All right, so take this rectangle here. If you look, we've got a rectangle that's a 4 by 6. So then you look here and the scale has gone 8 to 12. So if we were looking at the scale factor, we might say, all right, it's gone from the new length is 8 and the original length was 4. So we've got a scale factor of 2. Okay? Now, if you looked at the area of these rectangles, remember area is 6 times 4. If you did the area of that rectangle, that would be 24. Isn't it length times width for the area of a rectangle? And then if I go 12 times 8, I get 96. Okay, if you notice, if I compared 96, if I go 96 divided by 24, I actually get 4, okay? Now, if you notice, if you look at that, 4 could also be written as 2 squared. So what you're going to notice is that when you have if you had a length ratio, so these first one, that's called a length ratio because you're looking at the sides, okay? If you've got a length ratio of 2, when you look at their area ratio, you'll see their area ratio is 4. Or you could look at, say, it's the length 1 squared, yeah? Because it's 4 times, the area is 4 times bigger, and when the length is only 2 times bigger. So what happened if I said the length ratio, if I had said, all right, the length ratio of my similar figures is 3, what do you think the area ratio will be? How many times bigger do you reckon? Having a guess? I said that this was, that's how I got that. So what do you think? If I go 3 squared, what will it be? 9, good. So what if I said the length ratio was 4, what do you think the area one would be? 16. Good, it would be 16 because it's 4 squared. Excellent. So that's what we're going to start looking at, and we might use that fact to compare. So here it just says down here, you can see scaling areas. So the area is the length ratio squared. Really, you don't even have to ever remember the K and all that. Just remember the area ratio or enlargement is equal to the length 1 squared. Yeah? Okay, so let's have a look here. So we'll work out how we can do it. So two cuboids are shown and are similar objects. So they're going to tell you they're similar so that you know you can work it out this way. The height of the larger cuboid is 6 centimeters. We can see that. And the volume of this cuboid is 120 centimeters cubed. The height of the smaller cuboid is 1.5. And now it says determine the volume. So what can we do? We've gone straight to volume, but anyway. So if we look at the area ratio, the area is the length ratio cubed. I'm going to tell you now that the volume ratio is anyone going to have a guess? What do you reckon it might be? Yeah, good. Length ratio cubed. And I'll just show you now, before I do this example, I'll show you things. So if we had a little square, because they're easy to do. Okay, we've got a square and then we've got a bigger square, like this. Okay, so what if I said that one's length is 2, that one's length is 4? So we'd say the length ratio is 2, isn't it? It's 2 times bigger, yeah? All right, we can say 2 to 1 if you want. If you go their area ratio, we know it is, it should be 2 squared to 1, isn't it? 1 squared. So that would be 4 to 1. We said that. And that would make sense because this one's, if I looked at this one's area, wouldn't the area be 2 times 2, which is 4, if I was looking at the area of this? And the area of that one would be 4 times 4, which is 16. Isn't 16 divided by 4, 4? Yeah? So then if we looked at the volume of these two cuboids, the volume of this would be 2 times 2 times 2, which is equal to 8. The volume of the big one would be 4 times 4, which is 16, times 4, which is 64, yeah? Okay, so if you do 64 divided by 8, what do you get? 8. And see if you do 2 cubed compared to 1 cubed. What's 2 cubed is 8. So can you see how it works? And that's just to prove it. So we're going to now, so we'll do this example here and I'll show you how you can do it. So we now know that if we cube the length ratio, we will get the volume ratio. So looking at this question, we're going to look at the length ratio first. So they've said they're similar figures, and I'm going to say, all right, we're going to go new length. I'll make it a fraction instead of a ratio over old length. Oops. Okay. So we'll work it out. So we've got the new length is 6 and the old length is 1.5. If you do 6 divided by 1.5, what do you get? 4? Yep. Okay. So we've got a length ratio of 4 over 1. Okay. So now they want me to, I want to be able to find the volume. So the actual question is the volume of the small one. So I'm going to use the volume ratio. So if I've got the length ratio, the volume ratio must equal 4. You're going to cube both the numbers, yeah, of the length one. So because it's 1 cubed is 1, isn't it? Because 1 times 1 times 1. Okay, but you've got to cube both. And I would say, because that's a volume ratio, I'm going to say that's equal to, now, the big volume that I know over the little volume I don't know. That's what the ratio should give you, the same amount when you divide its actual volume by the other volume. So when you do that, so now you can just pop that into your calculator. You can have solve and you write 4. You can even leave that in the cubes if you like, equals 120 over x, and then you go comma x, and you find out what that is. We end up doing that, and we get x to equal the 1.9 centimeters cubed. Okay, so that's smaller than the other one, so that's good. So let's go a few more. So here, sorry, this is just summarizing it up. So you can see you find the length ratio first, okay? Then if you need the area ratio, you square it. And then if you need the volume ratio, you cube it. Can you make sure that you write a little note here? I really want you to make sure you're writing a little note here. Length ratio needs to be in its simplest form. So you need to make sure that, so before when we had the example, we had 6 over 1.5 has to be 4 over 1, okay? So even if you write a little note, just type it in calculator and press enter, and it'll simplify it, yeah? And that'll simplify it for you. If you don't simplify it, it doesn't work. So here, down here in the tables, they're just showing you, this bit here is if you are given this. So if you're given this ratio, the top one. So we have just been doing at the moment, we've been doing if we were given the length ratio. This is how you find out, you would go down this way to find out the other two. If you're given the area ratio, so say they said the area was a ratio, if you have to go back to length, that's how you find it. So if you have to go back to length, you do the square root, and then if you have to find the volume, you do that formula. So if you're given a volume ratio and you need to go backwards, that's how you can do it to those sort of things. You'll see questions if you get that. I'll show you. All right, so let's go and do a couple more examples. I'm recording it, boys, don't worry. The two triangles are shown as similar. The base of the smaller triangle has a length of 10 and its area is 4 centimeters squared. 40, sorry. The base of the larger triangle is 25 centimeters and determine its area. So we're just I'm gonna say in here, I'm just gonna call X, put the question, so X equals area of the larger. Yeah? So I know I need to get, because the area is the question, I need the area ratio. Okay? So I need the area ratio, but first I'll find the length. So the length ratio, so I'm going to say 25 over 10. Now, is that it's in its simplest form? No, it would be, what would it be? 5 over 2, yeah? So there's the length ratio. So I actually want to compare area. So the area ratio is going to equal 5 squared over 2 squared, all right? So when I'm going to go solve, I'm going to go solve, because I want to use the area ratio. I'm going to equals. Now, the big one is what I want to find out, isn't it? So I'm going to put the X there. That's along with the big shape. And the little one's what I already know it's 40, and then comma X. So what you're doing is making sure that across here is the same shape. From the same shape. It is, isn't it? That 5 squared is part of that 25 and X, yeah? So when you solve that, we'll get an answer. All right, so we get X to equal 250 centimeters squared. Okay? Yeah. Let's start this pyramid one. So 2 square pyramids are shown to be similar. So as long as they say those words, similar, we can use it. And then they've got the dimensions, and let's go look for what the question is. They want to find, So the first pyramid has a height of 9 centimeters and its volume is 48. So we might just pop above here that this one's volume is 48 centimeters cubed. Now the question is saying find the height and the volume of the second pyramid. All right. So is height a length or an area or a volume? What do you think? Good. Height's a length. So to find height, we're going to use the length ratio. Use length ratio. So we will get our length ratio. So length ratio, they would have given us two of the same things. So what did they give us? They gave us 5/4, yeah? So when you go to solve it, you're going to go solve. I'm going to put 5/4 equals. Now, I don't know the height of that one. That's what I want to know, isn't it? Height, and it should be the same as when I do the height of the smaller one like that. And I'll go comma H and I'll get an answer. So I get height to be 11.25 centimeters. Okay, to find the volume, we need the volume ratio. So let's get the volume ratio, which would be the length one. What do I need to raise what power to? Good, cubed. Okay, so then when we go and solve that, all we're going to do is solve, put the volume ratio in, equals the large volume is what we don't know, yeah? I'm just going to call it X over 48. We know the small one, and then we go comma X and find out the volume. Okay, so I got the volume X to be 93.75. So I would say that's centimeters cubed. Okay. Now, sorry, I've run out of room. I'm going to move this question. Okay, so let's have a look at a couple of the harder questions or the way they throw. So they say an inverted circular cone has a capacity of 100 meters cubed if filled with water to half its depth. So just to help you out there, when they say it is filled to half its depth, what you're actually getting told there is a little bit of a length ratio. So if you want to know, what you've actually got here is if you said that was 1, then if you're half the depth, wouldn't that whole thing be 2? Can you see that? Yeah? So really, and where the two similar figures that you've got is you've got the one with the water in it, and then you've got the similar figure is the whole big cone, the one with everything combined. So what you've actually got is a little length ratio there. You've got 1 to 2. So what they're giving you is a length ratio when they say that. So I'm going to, even if I do it this way, I'm going to say it's a 1, so it's a 2 to 1. So it's gone bigger. I might use that. Now, they said that the capacity of the, when half filled, is 100 meters cubed. So they're saying that, the capacity of this whole cone, so this volume is 100 meters cubed. They're saying the capacity of the whole thing can hold 100. And they're saying find the volume of the water. So you want to find this volume, so I'm going to call it X. So we're talking about volume, so we need a volume ratio. So if we go volume ratio, and I'm going to say 2 cubed to 1 cubed, and then I'll use that to solve it. I'm going to go solve, 2 cubed, I know that's their volume ratio. I know the big one's volume is 100 and x is the little one I want to know, and I go comma x and I solve that. And okay, so we get that, I should have just used the thing there. X is equal to 12.5 centimeters cubed. So that water there is 12.5 and the whole glass or inverted cone could hold 100. All right, so still the same. So here, here's another question. This is getting a little bit harder. So a cone has water poured in it as shown. What is the ratio between the volume of, now we have to be really careful here. They are asking me the volume of empty space to volume of water, okay? So we need to be careful. You can only compare, sorry, so this is a separate question. So this is this question. Okay, so first of all, we can only compare similar figures. So I'm going to use this water, like a water cone, and say it's similar to the whole cone itself, all right? Oh, sorry. All right, so they're talking about the volume, so we need the volume ratio. So first of all, we'll get the length. So we're saying it's 1 to 3. So if I say the length ratio of these two cones is 1 to 3. Okay, so if I was going to find the volume ratio, I'm going to cube those numbers. I'm going to say it's 1 cubed to 3 cubed, which is actually, what's 1 cubed? It's 1, and 3 cubed is 27. You can do it on your calculator if you need. So what I've actually found is, I would say, just for an example, I'm saying that the volume of this was 27. Say, I'm just making it up, and then we could say the volume of that is 1. That's what we're saying. If it was 1 centimetre cube, this guy would be 27 centimetres cube. So, but they want the ratio of empty space, so they want that one first, empty space to water volume. Okay, so if you have a look here, I do have the water volume, and I'm going to say that's 1. Now, in this cone is the water. If you took away the water, which would be 1, you'd be left with the empty space, wouldn't you? So how much empty space have we actually got? We've got 26. So the ratio of empty space to water is actually 26. Can you see how that was a little bit harder? That's getting a bit nasty, yeah? So they didn't want just the volume ratio. They wanted you to minus that and work it out. So there's an example. This next question, it says the ratio of the volumes of two similar shapes is 2 to 128. Find the length ratio. So first of all, you've been actually given a volume ratio. They're saying volume ratio is 2 to 128. We should still simplify this first. Before we do anything, we should simplify it, because that's not in its simplest form, is it? Because 2 goes into 2 once and 2 goes into 128 64 times, yeah? So we've got to simplify it. So now we want to go from the volume, we want to go back, this is volume, we want to go backwards to the length. So remember when we went this way, didn't we like cube it? Yeah? So if we go backwards, we want to cubic root it. So if you do the cubic root of 1 and the cubic root of 64, you'll actually find that it's 1 to 4. So we've found the length ratio. We're going to say that is 1 to 4. Now, if you're asked for the surface area is the same as area ratio. So how can we find the area ratio? We can. Can't we find the area ratio by squaring equals the length 1 squared, doesn't it? So I'm going to say it equals 1 squared to 4 squared, and you could just simplify that to be actual numbers, which would be 1 to 16. Excellent. So what is the scale factor of large to small? So if they want large going to small, so remember scale factor equals new length over old. So the large is the old, because they said large. So where's our length ratio? It was 1 to 4. So the large is 4 and the new length was 1. Yeah? So if they ask for scale factor, you need to use the length ratio. Length ratio must be used. Okay? Alright, I'm going to keep going. There's a few more. I'll pause. So a triangle has side lengths of 20, 48 and 52. A second triangle is similar to the first and has the longest side of 65. What is the perimeter of the second triangle? So you can find all the other sides using the length ratio. And the length ratio we can find by comparing two sides that we have that are the same. So if they gave me the longest side here, so I can use 65, and I say 65 over, what's the longest side in our first original triangle? 52. So 52. So you can say that that's the length ratio, and you might want to, does that simplify to anything? Don't know if it does. Yep, goes to 5 over 4. So now you know that that's the length ratio. You can find the other side. So to find, I'll say medium side, the middle size one, I'm going to say, I'll use the solve again. I'll go solve. I use the length ratio now because I know they all should fall into that category. I'm going to say I don't know the medium size over this 48. Okay, solve M, and that will tell me what that one is. So, let's work. Okay, I get M is 60, and then we're going to go find the last side, so find the small side. And you'll do the same. You go solve 5 over 4, and it should equal the small side over whatever it was for here, which was 20, comma S, and get the answer. Which is 25. So the perimeter of the big triangle will be 65 plus 60 plus 25. So what's that equal to? 150 centimeters. All right. Okay. Now, similar figures can also be used in maps, because really that's what you've got. You've got a map of what's actually happening out in the world. So it's all scaled. It's a similar figure. They've just shrunk the scenario. So when you get a scale on a map, that is like saying the length ratio. Okay? So you can work. So here, when they say, if you've got a 1 to 10,000, what they say, a distance of 5 centimeters on an actual map would actually respond to. So what that means, for every 1 on the map, it's actually 10,000 in real life. So if I've got 5 centimeters on the map, it's actually, you got to times that by 10,000, yeah? And so really, I've got 50,000 centimeters in real life. Now, would we talk in centimeters for that big? Nah. So I reckon we'd probably divide that by 1,000 to get meters. No, what would we do? 100 would give meters, sorry. So it's either, you might say it is 500 meters, or you might even say it is 0.5 kilometers. Remember, we I had those conversions in your notes. So we looked at them yesterday. Okay, and the last one, a model pyramid has a width of 4 centimeters and a height of 6 centimeters. If the real pyramid, so just draw a little thing. All right, they're saying 4 centimeters, height is 6 centimeters. Then they said in the real world, you got this big one. If it has a width of 60 meters, what will the height be? That's still just comparing length, isn't it? Yeah? It's like similar triangles. So we're just really comparing a length here. So we can just go, remember I said if you go 4 centimeters over 60 meters, would have to equal the same as when you go 6 centimeters over the height in question. And it will give you your answer in meters, because this is meters, this will be meters. So if you go solve 4 centimeters over 60 meters equals over h, comma h, and we'll find out. Okay, h equals 90 meters. So the height of the real pyramid is 90 meters. Does that sound reasonable? Yeah, so that's good. You should think about those things. So I think, I don't know, I've never seen the pyramids, but 90 meters sounds pretty good, so I'm going to go with that. So a land block has an area of 4,000 meters squares. When represented on a map, the block has an area of 10 centimeters squared. On the map, 1 centimeter represents the actual distance of. So what really they're asking, what they're asking here, this bit here, the actual question is asking you for the length ratio. Remember I said a scale on a map is a length ratio, and what you've been given is the area ratio. So we have the area ratio, they're saying, so they said 10 centimeters squared on map is equivalent to 4,000 meters squared in real life. Okay, so if you remember, when we went from, if we went from length to area ratio, what did we do? Didn't we square things? Yeah? So if we go backwards, what's the opposite? We square root it, yeah? But remember, we should always simplify first. So I'm going to simplify that ratio. I'm going to say 1 centimeter squared, because I've divided it by 10, is going to equal, are you happy for me to say that? Yes. I'm just simplifying 10 and 4. So if I've got that, and now what I'm going to do to get the length ratio, I'm going to square root those numbers. So square root of 1 centimeters squared, and then I'm going to do the square root of 400 meters squared, which would equal 1 centimeter. And what's the square root of 400? What's the square root of 400, boys? Oh my God. 20. Okay. Oh, sorry, we don't need square. So there's what is 1 centimeter would represent on the map would be 20 meters in real life. Okay. Well, here's the exam question. Okay, so this question is taken from the 2016 exam, and it was really poorly done. Well, it wasn't completed. Not many people got it right. So we really got to have a look at it, and it's to do with similar figures. So a string of 7 flags consisting of equilateral triangles in 2 sizes are hanging at the end of the racetrack, as shown in the diagram. The edge of the length of the black flag is twice the edge length of the white flag. For the string of 7 flags, the total area of the black flags would be. And then you can see that they're comparing the black flag to the white flags with their answers there. So what they've done there is they've told you that they're similar figures because they're both equilateral triangles, meaning so they're the same. So there's your clue that they're equilateral. And they're saying that the length of the black flag is twice the length of the white flag. So if we were looking at that, so say we've got our black flag here, and we just got our little white flag. So really we're saying a length ratio of 2 to 1, yeah, because it's twice the length. So we've got a 2 to 1 ratio. Now, then they ask us in the question, they said the total area of the black flags. So off again, people realise, oh yeah, good, we've got to find the area ratio. So we'll find the area ratio, which would be 2 squared to 1 squared, yeah? So, which is 4 to 1. So what you're saying when you say that area ratio like that, you're saying if, say, the black flag was 4 centimetres squared in area, you'd say the white flag was 1 centimetre squared, yeah? That's sort of what a ratio means. But what you had to be careful was you actually have, see here, you've got 1, 2, 3, you've got 4, so we've got the area ratio is 4 to 1, but we've actually got 4 black flags. And can you see we actually only have 1, 2, 3 white flags. So the area ratio in total for these two is actually 16 to 3. Can you see that? And that was the trap because there wasn't equal amount of flags there. So you had to be careful. So when they say for these 7, the total area of the black flag would be, so we're going to say it is 16 to 3 times the area. So can you see how I got that? So some people might have said 4 times because they're thinking it was just the ratio. So I would have guessed that B answer was probably the most common, but it's not correct. So it was a trap. Now you're looking at question 8, so it shouldn't have been that easy. So when the kids thought it was 4, you should have gone, yeah, no, something's wrong. All right, last questions. I've just put them in because you're actually up to the review chapter. I think that's why I've grabbed some couple of exam questions that can relate to this chapter. So we've got a golf ball is in a spherical shape. Its radius is 21.4 millimeters as shown. We're going to assume the golf ball is smooth. What is the surface area of the golf ball shown to 4 decimal places? So who can tell me using your formula sheets, what's the area of a sphere? Look it up. Area of a sphere equals... Pardon? Okay, area of a sphere is 4 pi r squared. So you simply just put in your calculator 4 times pi times 21.4 squared. Okay, whatever that answer is. I'm not going to work that out now. And then the golf balls are solid in the rectangular box and contains 5 identical golf balls as shown. What is the minimum length of the box? So can you see, if you've got a radius there, isn't that also a radius? So you've got 2 radiuses across each golf ball. Wouldn't that be the length of the box? So if you count them up, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So wouldn't we say the minimum length would have to be 10 times the radius? Yeah? So we're going to say 214 centimetres would be the minimum length that box could be. Okay? So you can see they're the short answer questions. Can you see they're easier, aren't they? The multi-choice are much harder. All right. So you can go do 17 review now as well for homework.